Let's extend our investigation into the effect of resistance on current strength and get more data and get a more solid investigation about this topic. To do that, we're going to use two circuits, one with a 12-volt battery and the other with a 25-volt battery. Both circuits are going to have an ammeter in the circuit measuring the current strength. Then we are going to vary the resistance of the circuit, and I'm representing that by using the symbol of a variable resistor, a rheostat. So let's open our simulation and let's build these two circuits. So we put our two batteries in, and the first one we're going to change the voltage to be 12 volts, and the second one 25 volts. Then we put a resistor in each and an ammeter in each. Obviously, we close the circuit with good conductors. And there we have the first circuit closed and we have the current strength shown. When I close the second circuit, how will its current strength compare to the first? Can you see it's higher? Why? Because we have a higher value of the battery's voltage. So the battery is pushing harder in the second circuit. And then what we're going to do is we are going to change the resistance of the resistors. And as we do so, we're going to measure the current strength. But before we do that, let's discuss what we are doing. We first need to write our focus question down. How does the independent variable affect the dependent variable for the context shown here? So what are we going to vary? Now be careful, between the two circuits that you can see there, we have voltage different. One is 12 volt and the other one is 25 volt. But that is going to come into our description of the context. So our context is going to be 4 series circuits with 12 volt and 25 volt batteries. But the thing that we are going to change is the value of the resistance inside the circuit. So that is going to be our independent variable. And then we're going to see how that affects the current strength, which we're going to measure with the ammeter. So this is our focus question. How does resistance affect current strength for 12 volts and 25 volt circuits? So what needs to be controlled between the treatments? Remember, the treatments are not the two that are shown there. The treatments are the different resistance values, and what must be controlled is the potential difference. In the first case, always 12 volts. In the second case, always 25 volts. And what is your prediction? How does resistance affect current strength? And how will it be different for the 12 volt circuit compared to the 25 volt circuit? And why do you say this? Then we need a table into which we can put our data. What should the heading of the table be? Table showing the relationship between what and what. For what context? And what should we have as our headings and our units? In the table columns. Table showing the relationship between resistance and current strength for 12 volt. That will be our first table, and then we'll have the same for 24 volt. And we have resistance measured in ohms, current strength measured in amperes. And then we have the same, but now for 25 volts. So we're going to have two tables. So in effect, we're having two investigations that we're going to run parallel to one another. So now let's go back to our simulation and let's collect our data. So now we have 10 ohms resistance in both cases. And in the first circuit, the current strength is 1,2 amperes, and the second circuit 2,5 amperes. Now we change the value of the resistance to 20 ohms for both of the circuits, for the second circuit as well. And we can see that in the first case, the current strength is 0,6 amperes, for the second circuit 1,25 amperes. We change the resistance of each of the resistors now to 30 ohms. First circuit's value 0,4 amperes. Second circuit we also change to 30 ohms. Notice how the color coding of the stripes on the resistor changes as well. And second circuit 0,83 amperes. 40 ohms. First circuit 0,3 amps. Second circuit 40 ohms 0,62 amperes. 50 ohms. First circuit 0,24 amperes. Second circuit 50 ohms 0,5 amps. Change the resistance to 60 ohms. First circuit 0,2 amps. Second circuit at 60 ohms 0,42 amps. 70 ohms 0.17 amps, second circuit 70 ohms, 0.36 amps. 80 ohms, 0.15 amps, and the second circuit 80 ohms, 0.31 amperes. 90 ohms, 0.13 amps for the first circuit, 90 ohms for the second circuit, 0.28 amps. 100 ohms, 0.12 amps for the first, and for the second circuit, 0.25 amps. 110 ohms, first circuit 0.11 amps, second circuit 110 ohms, 0.23 amps. Our last reading, 120 ohms, 0.10 amps, and 0.21 amps. So we need to put all that data into our tables. This is the data for the 12-volt circuit. Can you see patterns in the data? The most obvious thing that we can see is that as the resistance is increased, the current strength decreases. This is the data for the 25-volt circuit, and we also see the same trend. As the resistance is increased, the current strength decreases. And notice that these values are higher than the corresponding values for the 12-volt circuit. Remember that inverse proportion means that when one variable is big, the other is small, and as one variable is increased, the other one decreases by the same factor. So we can certainly see there's an inverse relationship. As resistance is increased, current strength decreases, but do they do this by the same factor? Now, if we look at the first two readings, we can see that the resistance has been doubled and the current strength has been halved. 10 times 2 equals 20. 2,5 divided by 2 equals 1,25. And we could look at other examples as well. But a nice quick way to determine whether two variables are inversely proportional is to check whether the product of the two gives a constant. So let's add another column to each of our two tables, where we multiply the resistance by the current strength for each entry. Pause the movie while you do this. And we do the same for the other table for the 25 volts. Again, pause the video while you do this. For the 12-volt circuit, the amazing thing is that whenever we multiply resistance by current strength, we get 12, which is the voltage of that circuit. Whereas for the 25-volt circuit, when we multiply a resistance by its current strength, we always get 25, which is the voltage of that circuit. So we have again confirmed the relationship between resistance, voltage, and current strength by showing that R multiplied by I equals voltage. Ohms multiplied by amperes equals volts. If we plot these two, we get these graphs. First of all, which of these two graphs is for the 12-volt circuit and which one is for the 25-volt circuit? How can you see that? Next, you need to give labels for the x-axis and the y-axis. And you need to complete the heading, graph showing the effect of independent variable on dependent variable. Graph showing the effect of resistance on current strength for V equals 12 volts and V equals 25 volts. Resistance is the independent variable, so it goes on the x-axis with its unit ohms. Current strength is a dependent variable, it goes on the y-axis with its unit amperes. The red line shows the 25-volt circuit data and the purple line the 12-volt data. How can we see that? Because the 25-volt data is always higher for a corresponding resistance than the 12-volt, because the 25-volt has a greater push from the stronger battery, making the current strength to be higher for a particular resistance. So what's our conclusion? How does resistance affect current strength? Resistance's symbol is R and current strength symbol is I. Current strength is inversely proportional to resistance, or we can say I is inversely proportional to R. And we can say more than that. Their product equals potential difference. I times R equals V.